Hello, today we are going to see how we can simulate radioactive decay by Monte Carlo method. This radioactivity is a random process. So here we are not going to apply the direct formula of the radioactivity, but we are using the Monte Carlo method to see how some specimen is decaying in time. Suppose there are a large number of nuclei at some particular time, so we say it is n at t. Then decay is random, and so this random process will be proportional to the number of nuclei. If the number of nuclei at any instant is very large, there is a large probability of decay in the number of nuclei. So here we have shown this as minus because as time goes on, the number will be gradually decreasing. Therefore, this change will be negative. That is, the number of nuclei will be decreasing as time increases. So, dn is the number of nuclei at some instant of time, and which is proportional to the number of nuclei present at that time. Then the probability of decay is proportional to minus dn by n. So if there are large number of nuclei, there will be large number of decay also. So the probability will be increasing. So the total probability will be, not the probability at any instant will be minus of dn by n at that instant. And so this we can write as minus dn by nt is equal to 1 by tau. So this is also a constant. So that constant we take it as 1 by tau. And this constant tau is called the mean decay constant, mean lifetime. Or decay constant we call it as a lifetime because it has a dimension of time. Now this is the decay at some instant. Therefore, suppose you want to find the decay, what is the number of nuclei which are decaying at some unit time. So we can take the probability of decay per unit time is the, we divide this by the time slot d by dt. So it will be 1 by dt, that minus of this quantity dn by dt. This unit of time may be any time unit, maybe second, minute, hour, day or year, depending upon the specimen. Some specimen will be decaying within seconds, so you can use dt as in terms of seconds. Sometimes you may be taking years to decay, so we take dt as in unit of years, like that. So you simply say that this is unit time, maybe in 1 second or 1 minute or 1 year, like that. Now we equate this. So 1 by dt into minus by dt will be equal to 1 by tau by dt. So dn by dt we take, then dn by dt, which n we can take the right side, which is equal to minus n by tau into number at time t. So here we have seen dn by dt is equal to minus 1 by tau dn by nt. Then dn by dt will be minus 1 by tau. You take this n to the right side and get it 1 by tau and time tau is called the mean time constant. Then we can simulate the radioactivity using Euler's algorithm. We are going to solve this equation, which is the simulation. We are finding the number of nuclei at any instant of time by using Euler's method. So the Euler's method you already know, but even then, now only to show this, to estimate the error in this calculation. So we expand this function using this Taylor series expansion of a function n at t plus delta t is equal to n at t plus derivative of the function at t into delta t plus delta t whole square into second derivative divided by 2 factorial, like that. Here we are ignoring this term, so the error in this case will be of this order. Delta t whole square will be error in those order. We are taking calculation delta t as h. So in this case, the error is of the order of h square. Now we are ignoring this, and now we get as nh t plus delta t c nh t plus dn by dt. So we substitute for dn by dt, so it will be nh t plus nh t plus dn by dt is equal to minus 1 by tau into nt into delta t. Here this delta t, and dn by dt is equal to minus 1 by tau delta t. So you can see as time progresses, the number gradually decreases. So we can find this at another time step. This way we gradually increase the time till the required time is reached. And the Python program we can use to calculate this, and you can store the values at any instant in a Python array or list, then you can plot the graph also. You plot, you will be getting a graph like this. This is as time progresses, the number of nuclei gradually decreases. This is an exponential decay, and which is the decay as specified by the analytic formula. So we are not using any analytic formula, but simply using the numerical value, which is agreeing in quite agreement with the analytical value, as the n is equal to 0 d power minus lambda t, this is like that.